So if it is a binary classification model, what would be the value of y? Y would be a real number, right? Y would be a real number and it can take the value either 0 or 1. The classic example of this binary classification is tumor, if it is malignant or not. So the y is not a vector, y is not a matrix, y is a scalar, and the value of the y can be either 0 or 1. That is what it is. That is why h theta of x, that is the derived value, y as well as the derived value, both are a real number. They are neither vector nor scalar, nor matrix. They are only a what do you call it? It's a real number. And if in the case of a multi-classification model, the output y, is that going to be a vector, or is that going to be a scalar, or is that going to be a real number? Any guess? So we saw that for binary classification, y as well as the derived
vector.
Exactly, vector. So we saw one example. So in this particular case, you can see that it is a vector. Vector with how much dimension? The dimension of the vector is k. Because if there are k classes, there will be the dimension of that vector is going to be k. So in this particular case, there are 4 dimensions. Remember the example we have selected earlier was pedestrian, car, motorcycle, or truck from an image recognition program. So if that is the case, the output value, either the observed value or the actual derived value, would be a vector, not a scalar. And the dimension of that vector would be k. K means that many output units are there. So that's what it is. So hope this is clear. If this is not clear, let me know, because this is very important. This understanding is very important. And then we talked about the cos function. So what we did was we took the cos function we had, the j theta of the logistic regression. And logistic regression, the cos function is this. It sums up all the individual cos of all the training examples and then divided by m. This is why I'm just again and again I'm highlighting what is m, what is all these variables I'm highlighting, because this notation is very important. And different classes, for example, if you go to the Columbia, they have a different notation. So it's very important that you're grounding on the notation, whatever you are following. So the first part is this, and the second part we added something called regularization. And why do we use regularization, if anybody can tell? To avoid 2 problems. What are the 2 problems, if you remember? Exactly, overfitting or underfitting. And what exactly is this cos function represents by any chance? Forget about these complex logarithm and all those things. But simple terms, what exactly is this cos function represents? Because you don't need to study this equation by heart. You don't need to remember this. All these you can pick up, but
it's basically the error, right?
What is that?
It's basically the error.
Exactly. The difference between the observed value and the actual value. That's what it is. So basically, it is the sum of the average of all the errors of all the training set. Can I say that? And if you remember, I introduced something called a loss function, and then I introduced something called a cos function. I didn't highlight it, but just wanted to make sure that the error of a particular training sample is known as loss function, and the aggregate average of the errors of all the training set is what is called cos function. And this is what needs to go to your head. That's it. You don't need to worry about anything. And then from there, when it came to the neural network, one of the differences in the case of a logistic regression, the output was always a binary. But in the case of a neural network, the output can be a vector, and the output can have k number of outputs. So here, what happens is h theta of xi represents the ith output of the ith sample in the training set. Jeevan already answered that. That's what I was asking. Like x5, y5. where Y5 represents the actual output of the fifth sample. H theta of X of 5 represents the calculated output of the fifth sample. That's clear, right? So here the difference is this equation is modified because we introduced one more summation, because here that summation was not there because there was only one output unit. Since we have k output unit, this loss function as well as the cost function has to be accounted for the errors occurred in each of the output units, and that is why this sigma is added. The sum of the k output units needs to be added. And then the loss function, sorry, the second factor, which is the regularization parameter, has to be accounted for all the theta, because earlier there was, for one input unit, there was only one output unit, one output weightage, because one input unit has only one weightage. Here in the case, one input unit can have multiple weightages, each one for the next output unit. So what happens is this theta becomes a matrix. So the theta Lji means it is a matrix. It is not a vector. It is not a scalar. It is a matrix. And that is why this additional factor come into the picture. This I, this part come into the picture. And that is what is this regularization parameter. Don't worry about that. You don't need to remember this. I was just trying to explain what exactly it means. So when you convert the cost function from logistic regression to a neural network, the major change is going to be one is on this particular part where you calculate the cost. When you calculate the cost, the logistic regression accounted only for one output unit, whereas the neural networks can potentially have k output units, and if that k output unit is there, this additional summation is required. And for the parameters theta, what happens is the parameters in the neural network is a matrix, not a scalar. So that is why this additional summation is required. So this is cost function. So from this cost function, so the notes I put that note there. So once you have the cost function, so remember the process is initially develop the model. From the model, have the cost function, and then adjust your parameters in such a way that the cost function is minimum. So here you calculated the cost function as j theta, and this is the equation which we had in the previous slide. And what we are trying to do here is minimize the value of theta, j theta. And remember, it is for all the value of the thetas. So the j theta has to be minimal considering all the values of the parameters. And here the problem is the parameter is not a scalar. In the case of simple logistic regression, it was a vector, right? Because if there was x1, x2, x3, the parameters was theta 1, theta 2, theta 3. And typically the bias unit or that base unit was x0. If that is the case, x0 theta 0, x1 theta 1, and x2 theta 2. So if you take theta as a whole, it was only a scalar, because scalar means it is the collection, it is a one-dimensional matrix of all the input parameters. So it was theta 0, theta 1, theta 2, and theta 3. Basically, that is a vector. But in the case of a logistic regression, if you remember our previous classes, I tried to highlight the fact that the theta is a matrix, not a vector. Matrix means it has a row and column, because if you remember that big equation, right? Theta 1, 1, 0, theta 1, 1, 2, theta 1, 1, 3, theta 1, 1, 4, and theta 2, 1, 0, theta 2, 1, 1, theta 2, 1, 3, theta 3, 1, 0. So if you take the end, because typically here what you have is not just the input and output layer, you have hidden layer, and each layer can have its own parameters. So considering all that, and each parameter can contribute to n number of other parameters, because considering that theta is a matrix, and theta is of the dimension I comma means ij, and like this is how Lij, because L would be the number of rows, and then you can have that many values. So that is why when you try to calculate the gradient computation, you have to minimize the j theta for every value in that theta matrix. So that is what the goal is. So is that clear? So first of all, you need to minimize the cost function to the minimum possible value. That is what the gradient descent does, right? The gradient descent computation does. So here, how do you do that? You need to find out j theta. For all theta, it has to be minimal. And for that, what you have to do is you have to do the partial derivative of j theta for all the values of theta. That is what it is. Is it clear?
Yes.
Okay, wonderful. That is the complicated part. So now let's go and do the gradient computation. So the gradient computation, how it is calculated is you wanted to calculate the partial derivative of j theta for all the values of theta. So we said, like, initially what you have to calculate is you have to calculate the activation value of all the nodes, and then through a forward pass, and then you have to do the partial derivative calculation through a reverse backward pass. So we remember we talked about that in detail. We did little bit of understanding of the differential equation also, as how to calculate the partial derivative, etc., by taking a simple example. So let's try to understand this. So in this case, what happens is, let's take one training example. Just listen this very carefully. You need to understand this intuitively only. So how do we calculate the forward propagation is what we are going to explain now. So let's take one training example, XY. So what would be the input layer? So the input layer is 1, 2, 3. So what would be this X? Is this a matrix or a scalar or a vector?
It's a vector.
Excellent. That's what it is. Everybody is clear? So that's exactly what is represented by this X. So what would this A1 represents the layer 1. A2 represents layer 2. R3 represents layer 3. A4 represents layer 4. Where I'm still not 100% convinced or is your understanding of the scalar and the vector. So when I say this A1, is that a vector or a scalar or a matrix?
It's a vector.
A1 is a vector.
Beautiful. So if I say A11,
That's a node. That's scalar.
excellent. And if I say A,
That's again a vector.
it's a matrix, because when I say,
Oh yeah, it's a matrix. Yeah.
right,
Yeah.
it represents A1, A2, A3,
A3 and A4. Yeah.
4 scalars. Scalar 1 is A1, scalar 2 is A2, scalar 3 is A3, scalar 4 is A4. So understand this. This is very important. When we were reviewing scalar, matrix, and vector, you would not have even imagined that how important it is. Look at this. This is very important. So A is a vector. A1 is a, sorry, A is a matrix. A1 is a vector. A11 is a scalar.
Scalar.
So I can say that the matrix A is I can say that it is a collection of four vectors, A1, A2, A3, A4. And A1 is a collection of 3 scalar, which is 1, 2, 3, and like that. So that's what it is. So now, when you say X is a vector. And what I means, as essentially you don't have to calculate this value of A1, because the A1 is the input features, correct? That is what it is. A1 is the layer 1 or the input layer. So basically the vector A1 is nothing but X. Is that correct? A1 equal to X. That is the first step.
Yes.
Yes.
So what it means is A1 means A11 is going to be X1. A12 is going to be X2. A13 is going to be X3. In this particular case, X is a vector which consists of 3 individual nodes. Clear?
4 with the bias.
Yeah. With means if there is a bias, it is 4. Absolutely, you're right. Clear, right? So this is clear. Scalar, matrix, and vector. That notation is clear for this, right? So you
Yes.
got the value of A1. So once you have A1, your goal is to calculate A2. And mind you, A2. So how do you calculate A2? A2 is calculated in 2 steps. The first step is you calculate the Z value. The C value Z2 is nothing but A1 theta 1. So theta 1 A1 is what is called Z2. And then for being a classification model, this Z function has to go through another modification. And what is that modification? What we call it as sigmoid modification, right? So theta 1 x1 was the traditional model, which has to go through a transformation called the sigmoid, because otherwise the local peaks and value will come and the gradient descent will fail. So first you have to calculate Z2. Z2 is nothing but theta 1 A1 or theta 1 x1 in the old notation, because x1 is nothing but A1. And so A2 is calculated by taking the sigmoid function of C2. So G of C2 is essentially A2. So this is how you calculate A2. So the question is, C2, is it a vector or a scalar or a matrix?
That's
Going to be a vector.
Exactly. That's it. So what about A2? A2 is also a vector,
Yes.
because what happens is the sigmoid function will transform every element of the C2 vector into a new value. That's it. And if you remember, there is a formula, right? If G of Z equal to 1 by 1 plus e to the power, remember?
Yeah.
That's the formula. So that transformation will come, and that is how you get A2. And what you do to G1's point means you can add the, at this point of time, here you can add one actually bias unit. Here also you may want to add a bias unit, and that will be added. And then once you have this A2, what is the next step? What would be the next step? So initially from X, you calculated A1. Using A1, you calculated C2. And using C2, you calculated A2. And the next goal is calculate A3. How do you calculate A3? Can you tell?
So before going to A3, we need to have Z3, right?
Exactly. Exactly. That's what.
Oh,
So how do you calculate C3?
again, sigmoid functions for hidden layer 2.
No. Actually,
new weights.
A2 times theta 2. That is what is going to be the value of C3. Remember, that's exactly what you did. And then apply the sigmoid function of C3. That is going to give you the value of A3.
Oh, okay. First we have. Okay.
Yep. Yep. So once you have it, the next goal is calculate A4. How do you calculate A4? First, you have to calculate Z4. And from C4, what do you need to do? You need to calculate using the sigmoid function. You need to calculate G of C4 equal to A4. So the forward pass, you have to calculate from the input layer. You have to calculate the first hidden layer. Then you have to calculate the second hidden layer. And then you have to calculate the third hidden layer. And it has to go through until you reach the end. So this is the forward pass. You just need to remember this much only. this is good enough for you to get a clear picture. So once it is done, the next part is the backward propagation algorithm. So the backward propagation algorithm, how it starts from the last layer. It starts from the last layer, and then you go back to first the next layer, go back to next layer, and finally you go back to the initial layer. So here the intuition, or essentially what you're calculating, is something called delta L of J. Delta L of J indicates, means, remember what is the superscript always represents?
Layer.
Layer. So in this particular, delta 4 represents what? It is the error in the node 4, or sorry, the layer 4. The error of layer 4 is represented by this delta 4. If I say delta 4, is that a matrix or a vector, or is that a matrix, vector, or a scalar?
Vector again.
Exactly. So delta 4 is what? It constitutes of delta 4 1, delta 4 2, delta 4 3, and delta 4 4. This is a vector, and the elements of that vector is like that. So let's say, how do I calculate delta 4 1? So the delta 4 1 is calculated because we have two values, right? One is we got an activation value, which is called A4 1, and then you have an actual value based upon the training set. For example, if this was the jth element in your training set, then what do you do? Like, if this was the jth element, what do you do?
YJ.
Yeah, so the actual value minus.
The.
So what you do is A4J, A41 represents the actual value of this node from the training set. Sorry, I made a mistake. A41 represents the calculated value for that node in the training set. And Y of 1 represents what?
The actual value of the
Value.
yeah.
So you take the difference. That is essentially what this error of that particular layer. So like that, you need to calculate the entire vector. So
Ish,
yeah,
don't we square the error?
no, see, yeah, means you can square the calculation, but here what happens is, means that is for the traditional gradient descent, you square, but I was talking intuitively. So
Okay.
basically what you do here is it's a logarithmic function, right? So remember the cost function. This is the cost function here, right? And this particular portion, G1, represents the actual squared error part, whatever you see.
Okay. Okay.
Okay, so even the idea of squaring is for what?
To
negate the effect of signs.
Yeah.
When you sum up. So that's the reason. So just intuitively understand that this delta represents the error of node J in layer L. So if I say that delta 41, it represents the error of node 1 in layer 4. That is what? Because you need to go back. That is why the symbol is very important. So the first error calculation is very simple. Just like the first activation calculation of the input node is very simple. Because the input parameter, input features is basically the first value of the activation node. Like that, the output feature, means the observed value minus the calculated value directly give you the error of the final layer. So the calculation of the first errors of the final layer is very simple. Is this clear? This part is clear. Means delta 4 of J equal to means A of 4 of J minus YG. Is that clear?
Yes.
Okay, great. Now let me ask you a question. How do you got the A4J?
It's from the forward propagation.
Exactly. That's it. So you started with A1 and using the forward propagation, you derived the A4. So in fact, A4 is a derived parameter, sorry, derived value. And for calculating the A4 only, you needed the forward propagation algorithm, correct? So the gradient computation in the case of a neural network has two major steps. One is the forward propagation step, and second one is the backward propagation step. The forward propagation step is going to give you all the activation nodes, whereas the backward propagation step is going to give you the actual error value at the beginning node. That's what it is. So now let's see how to calculate this delta 3, because delta 4 was very simple, because delta 4 can be calculated with the difference between the actual value as well as the derived value. So delta 3, there is a formula, and that formula is very straightforward. It tells theta 3 is a vector or a matrix, or what exactly it is, this theta 3.
Weightage. It's a matrix.
Weightage.
Is it a scalar or a vector or a matrix?
Can be a
Matrix.
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 Theta 3,
Matrix.
theta 3 is a matrix or a scalar? Remember? It's a matrix. So don't worry about that. That is very true. So it is, if you take all the parameters associated with, because for example, if you take the theta associated with this node, how many thetas will be there? There will be one weightage for this node to this node. There will be another weightage for this node to this node. There will be another weightage from this node to this node, from another weightage here. So there are 1, 2, 3, 4 weightages are there for this nodes. If this is x3 or x, whatever it is, that x0, and if this is x1, how many weightages are there? Again 4 is there. So for each one, there is 4 weightages there. That is why theta is a matrix. So then what do you do? This theta 3 transpose, you take the transpose, and then you take the value of this error in the fourth layer. Then this is a special symbol. In matrix, if you put like this, do you remember, anybody who studied in the matrix class? There are two types of multiplication in matrix, and the traditional multiplication of matrix is what? Every element will be multiplied by all the different things. So if you use this symbol, it means element wise multiplication. So what do you mean by element wise multiplication?
Same cells get multiplied.
Exactly. So that is what it is. And then this sign is known as G prime. G prime. Earlier, we had the G of Z3, right? Means we used the G of Z3 for the calculation of A4, if you remember. If you remember, A4 is calculated using how? G of Z3. And C3 is what? Essentially, basically?
Theta 2.
Yeah, C3, remember, don't forget, C3 means theta 2 times A2, and A3 is calculated by G of C3. So here, what you do, G prime of C3. G prime of C3 is nothing but a partial derivative of C3. A partial derivative of C3. So this is the formula. So this is the general formula. So the error means this is a vector. The error vector on the third layer is equal to the parameters. You have to take all the parameters on the third layer, transpose it, multiplied by the vector of error in the fourth layer, element wise multiplication to the G of C3. Means G meaning, again, it is a partial derivative. G prime of C3. And the value of that is essentially this. This is the derived value. Don't worry about this. Just remember this. That's it. So A3 times element wise multiplication 1 minus A3. This is the formula. So don't worry about this. Just understand that this is how you calculate. So you calculate this error here. and you propagate that error backwards. And if you remember, I took one example. Remember, if you I said like A plus B times C equal to D, and then I drove the node and I saw why do we need to do the partial differential equation, right? So we wanted to see how much these final nodes changes when there is a small change in the parameters associated with the initial nodes. So that is what we wanted to calculate, and that is essentially what this is calculating. So the error in layer 3 means what exactly, because the challenge here is you just need to visualize this very carefully. The layer 3 means layer 4, it's very simple because you have an observed value. You have an observed value to calculate the actual. Layer 3, you have a derived value, but you don't have an actual value. You got it, right? Layer 3 do not have an actual value. So basically, to calculate the error in layer 3, you have to calculate an actual value from the actual value of layer 4, and then you have to minus that with the actual derived value. So that's what this is being done. So A3 element times element wise multiplication 1 minus A3. So that is how the error in the layer 3 is calculated. And then you calculate the error in layer 2. It's the same formula, theta 2 transpose delta 3. Here it was delta 4. And then G prime of C2. This is what it is. And essentially, when you come to the first node, there is no error. Why there is no error?
You have an
It's
actual.
inputs.
You have an actual input, so that is why it is. So this is how, because the calculated value of layer 1 and the activation value of layer 1 is the same. So naturally there is no error. So this is what it is. So this is how, and basically this represents actually the partial differential of the cost function. So it can be written as, so what exactly is the sum total of the partial derivative of the j theta? So just need to, means if you know the calculus, you can derive this. But if you take the formula, it is A of Lj times delta of L plus 1 I, because it starts only from the second layer. So this is what is there. So
Rajesh,
yeah.
Rajesh,
Yeah.
quick question. See, if you go back to the delta 3, and
Yeah.
what we are saying is we are trying to derive what the layer 3 is going to be, right? I mean, going backwards.
Error of layer 3.
Right. So right, we are trying to find the error of layer 3.
Yeah.
Since we don't have an actual value, we calculate what the layer 3 value should be.
Layer 3 error should be whatever is the layer 3 error, right? So you have an A3. A3 is the calculated value of layer 3, but we don't have, because if it is layer 4, how did
We
you
have an
calculate
actual value and
have
a
an actual-
calculated value.
Correct. So now the problem is you don't have an actual value for layer 3 because layer 3 is an imaginary node or
Correct.
a hidden node or a
Right.
derived node.
Right.
So what you have to do is from layer 4, you have to backward propagate what could be the potential error. So it is a error of layer 3 is only a calculation, whereas the error of layer 4 is a reality. So based,
Okay.
yeah. So remember, like visualize this like this, because layer 4 is the actual projected output.
Correct.
But layer 3 is a learned feature, and the learned feature can have error, and there is no way to calculate it directly. So you have to calculate that indirectly. So probably means I was listening to Andrew NG. He tells me that he tells to the public that out of all the time he spent on machine learning, deep learning, this is one of the most difficult topic he had ever encountered. So that shows the depth of this topic. And for you to do the programming, you don't need to know or any of these calculations, but definitely you need to know how we are doing it. So please give an understanding of the architecture of the neural networks, understand how the forward pass works and why you need the forward pass. The forward pass is basically deriving the calculated value of the output nodes as well as the hidden nodes, right? And why do you need the backward propagation? Because the error of the final node can be calculated, but the error needs to be backward propagated to calculate the cost function, because cost function is the aggregate holistic error, because that is what
Okay. Yeah. Okay.
that much is clear.
Yeah. Yeah. So basically what we are saying is we are just, in order to get the sum of all the errors for is why we are really trying to do it, because the error is the sum of the errors is your cost function.
Yeah.
Right. And right.
Exactly. That's it. So now let me complicate matter further. So whatever we did so far was an oversimplified version. We did this only for one training set. But practically, you cannot calculate the cost function, or you cannot train a model just with one item, one actual value, right? One item in your training set. The training set will have m different values. So how do you modify this cost function? How do you calculate this cost function for a set of m values? So that is the next step. By the way, you can Google this backward propagation algorithm. You will see how complicated it is. People get completely confused. So if you understood just whatever we said, that is really, really good. So why I'm telling this is, if you don't understand this, if you need to ask offline questions, it is okay. And don't, I had to study this 6 or 7 times to get this idea. I'm just telling myself, because this is very complicated.
Rajesh, can we go back one step, please?
Yeah.
In this, when we're calculating delta 3, we have the G prime of Z3.
Yep.
Now, my question is, what exactly does this signify? Now, in the first part, we have the weightage multiplied by the error. So that brings us back to, it just gives us the error, right, for delta.
Yeah.
But what is G prime doing there?
G prime typically
of Z3.
Yeah. So what is the G prime means what? It is the different means it's a partial derivative of C3. So if C3, what is C3 represents? C3 represents the key input used to calculate A3. Is that correct?
Yeah.
C3 is the key input that determines the value of A3. And C3 is derived from the previous layer, because the previous layer's parameters plus multiplied by the activation function of the previous layer is what is going to give you A2 times theta 2 is what is C3. And C3 is the key input that is going to determine the value of A3. And the theta 3 transpose delta 4 is going to give you how the parameters on the layer 3 is impacting the, means it is multiplied by the error calculated in the layer 4. And now what exactly the G prime C3 represents is, if you remember the differential equation, what exactly the differential equation is going to tell you, derivative is going to tell you. So if I say that derivative with respect to time, just remember the definition I told you at that point of time.
Small change.
If I say that
minimum value.
Yeah. So for example, G prime of theta, right? So when the theta changes in an infinitesimally small amount, what would be the change of C3, right? So the theta, when it changes little bit, how the Z3 is going to change. So that is, it is basically calculating the influence of those parameter on layer 3, because we took C3, not A3, because to avoid complication, because if the C3 changes, accordingly the A3 changes. So we wanted to see how much would be the impact of each parameter on the layer 3. And that is multiplied by the parameters of that layer to the error of the fourth layer. So how that error is backward propagated is determined by the influence of parameter on that particular layer. So the derivative of C3 is going to tell you how much that layer will be impacted if there is a small change in the thetas. That is what it is. So, and just keep that and the meaning of the, because that is exactly the reason why I spent some time and explain the meaning of differentials. So think about this, right? Like a change of distance with respect to time. And if you remember, the example I used is your speedometer. So if you look at your watch at now and look at the speedometer, technically it cannot happen because the speed is always determined by the distance traveled divided by the time. So that is where we use the calculus. The calculus uses an approximation, infinitesimally small amount. Actually, if you really look at the calculus book, it tells 0.00090 plus that 1. That much change when it happens to the independent variable. So how much the dependent variable changes. So this is what it is. So to put in perspective again, we wanted to backward propagate the error. So the error in layer 4 means the layer 4 will be backwardly propagated because the connection between layer 3 and layer 4 is the weightages, and that is why the theta 3 is multiplied by the scalar of error 4. So because how much the error will be backward propagated, it will be determined by the theta, because the layer 4 is derived using the weightages for each of the values in layer 3. And then we wanted to see how much the layer 3 itself is influenced by the changes of the parameters. So these two together constitutes the value. And if you want to derive it calculusly, means with calculus, there are derivations, and I can send you that. I have it, but there is no need to study that much. Just intuitively understand. But it's a good question. Let's go back. So now we are going to see how this backward propagation algorithm is going to work. So we are going to introduce a diff delta. There was a small letter delta, that is what we saw earlier. This is small letter delta, and this is capital delta. Capital delta represents the aggregate, small delta represents the error of one training set. Capital delta represents the error of the entire training set. So that's what it is. So initially you initialize that as 0, and then you start a for loop. And within the for loop, what you do, you calculate the exact same thing we did earlier. You calculate the error of a single function. So you calculate that. So initially you set AI equal to xi, because that is the input node. And then you do the forward propagation and compute all the layers. And then using yi, you can calculate the error of the final layer, because the error of the final layer is the actual value of the final layer. Sorry, the calculated value of the final layer minus the actual value. And then you calculate all the backward propagation up to delta 2, because delta 1 you won't calculate, keep that in mind. And then basically you calculate that cost function of that particular layer is the initial value. When you take the first value, this is 0. So basically this is the cost function, means how do you derive it? If you remember, that is exactly what we came here. So here we calculate the first value and iterate to the second value. And when you do the second iteration, already there is a value for this, and the next error will be added here. And finally, when you iterate all the value, you get the final delta L. And the final delta L, which is means it is the individual delta L, and all this is how you calculate each time. Because if you take this as a scalar, this is how it is. And finally, you get the delta, And once you have the delta, this is the final value of your error function. So the error function is it is 1 by m delta Lj, and if it is j equal to 0, j equal to 0 means it is for that initial parameter theta 0. For theta 0 only we apply the lambda if the regularization is there, and if the regularization is not there, this is the value. So if you are not considering the regularization, the partial derivative of your cos function for all the parameters of theta, it is going to be this d value, and this is how the d value is. Dij equal to 1 by m delta ij, because you basically what you did was you calculated the individual error of each training set, summed it up and divided by m. So this means you are doing the average. So this is how it is. Don't worry about the calculations, but intuitively understand. So if I summarize, if I pause here and summarize it, what we did was initially we created the neural networking model, and we spent a lot of time in understanding the neural networking model. We understood the input parameters, we understood the input layer, we understood the output layer, and we have calculated all the hidden layers. And we spent a lot of time in understanding how these activation nodes work, because the input layer and then there is for each layer, each node, there is a vector, because the parameters is a vector. Because let's say that initially you had 3 input layer and 3 activation layer. Activation layer 1 is determined by a vector of theta, and that if you take that layer completely, it is a matrix of theta. So that is what we calculated. And if you remember, just go back to the previous lecture notes. We explained that a lot, and we calculated how that theta matrix is calculated. We discussed that. And once the model is created, we said we need to do, means how are we going to do the cost function and optimize the model. To optimize any model, first you need to derive the cost function. So we derived the cost function, and then once the cost function is derived, what you have to do is you have to minimize that cost function. And how to minimize the cost function is take the partial derivative and make sure that that is minimal. Partial derivative is the rate of change when all the theta changes. And calculate this partial derivative, you have to do a forward propagation, and the forward propagation is going to give you the activation vector of the final node. Once you get the activation vector of the final node, you have to calculate the error vector of the final node. The error vector of the final node is very easy, because the activation vector of the final node minus the actual value is going to give you the error vector of the final node. And then it has to, this error vector has to go back. You have to calculate the error vector in each of these previous layer until the beginning. The first layer will not have any error vector, and using that error vector, you calculate the actual partial derivative. So there is a formula for that. We discussed it. And then this is going to give you the partial derivative or the cost function of one example. And then that has to be aggregated for every item in the training set, and you have to take an average. My God. Is it intuitively clear at least?
Conceptually, yes. Thanks.
Yeah,
that's all you need. So that's exactly what is intuitively. So you don't need any derivation, but if this is clear, that's fantastic. This is where you make a difference in the interviews if you go for a good role in machine learning. So they know that you know this in detail. Okay, so it's 9 o'clock. So we will pause here, and we will continue this topic. One more class, we will be done with that, and then we will go to the next topic. So how do you want to proceed? So once we cover the neural networks, do you want me to continue all the other theory, or do you want us to catch up with Python and do this much and then proceed? What do you say?
Let's get the theories all down.
Done? Okay, that's fine. Okay, so parallelly, just
Rajesh, can we catch up with the theory first?
yeah, that's what.
So there will be continuity.
Yeah, sure, that's fine. So we will finish the theory first, and even if you know this theory, this is really good, and this is going to help you a lot. So parallelly, if I can suggest some of you, just do the Python. And Rajesh, actually, there is one good book Kailash ji posted on Python practical samples or something like that. Let me open that book. I was looking at that.
Yeah, we had shared that in the group. Yeah.
Yeah. So if you can just do those samples, that would be really good. They are elementary samples, but it gives you a handle on the Python. Okay. Excellent. So thank you, and we will talk next week.
Sure.
Thank you.
Thank you.
Rajesh, thank you.
Good night.
Thanks, Rajesh.